This is the second video of Unit 2 flow through duct. The topic is variation of Mach number with the duct length. The duct length required for the flow to pass from a given initial Mach number m1 to a given final Mach number m2 can be obtained from the following expression. Mean friction coefficient with respect to duct length is given by F equal to 1 by L max integral of 0 to L max f of dx into f of dx from 4f dx divided by d equal to 1 minus m square divided by gamma m square into 1 plus gamma minus 1 divided by whole power m square into dm square divided by m square. Integrating the limits are x equal to 0 to x equal to L max, then m equal to m to m equal to 1. So the final derivation is 4 f of L max divided by d is equal to 4 f of L max divided by d into m1 minus 4 f L max divided by 2 into m for m2. So it is a first problem. Problem number 1. Air flow through a pipe of 300 mm diameter at inlet temperature is 35 degrees Celsius, pressure is 0.6 bar and stagnation pressure is 12 bar. At a location 2 meter downstream, the static pressure is 0.89 bar. Estimate the average friction coefficient between two sections. Given data: D equal to 300 mm, T1 equal to 35 degrees Celsius, P01 equal to 12 bar, P2 equal to 12 bar, P01 equal to 0.6 bar and P2 equal to 12 bar. So P1 divided by P01 equal to P1 0.6 divided by 12 is equal to 0.05. From Fano table, P1 Mach number at P1 divided by P01 equal to 2.6. Then to find out the M2, we know that 4 f of L max divided by d for m equal to 2 is equal to 0.453. Then P2 by P1 is equal to P2 by P star for M2, P2 by P star for M1 equal to 2.6. Then find out the M2 at 0.479 equal to 2. Then finally 4 f of L max divided by d for M1 equal to 2.6 minus 4 f of L max divided by 2 M2 equal to 2 is equal to 0.453 minus 0.305 is equal to 0.148. So this is the, then 4 f of 2 divided by d power for m equal to 2 is equal to 0.148. Then f equal to 0.148 into 3 divided by 8 is equal to 5.5 into 10 power minus 3. So this is the friction coefficient. Then the second problem: a circular duct passes 8.25 kg per second of air at an exit Mach number of 0.5. The entry pressure and temperature are 345 kPa and 38 degrees Celsius respectively, and the coefficient of friction is 0.0005. Full stop. If the Mach number at the entry is 0.15, determine diameter of the duct, length of the duct, pressure and temperature at the exit, and stagnation pressure loss. Given data: m equal to 8.25 kg per second, m2 equal to 0.5, p1 equal to 345 kilopascal, T1 equal to 311 Kelvin and F equal to 0.005 and M1 equal to 0.15, M1 equal to 0.1. Then diameter of the pipe, first one find out the diameter of the pipe. We know that M equal to rho AC, then rho 1 A1 C1, then M equal to P1 divided by RT1 A1 M1 root of gamma T1. Then m equal to P1 A1 root of gamma m1 divided by root of rt1. Then a1 equal to m root of rt1 divided by root of gamma m1 p1 is equal to 8.25 root of 287 into 311 divided by 345 into 10 power 3 into 0.15 root of 1.4. Then a1 equal to 0.040253 meter. Then we know that area equal to pi by 4 d square. Then d equal to 0.226389 meter. Then find out the length of the pipe. From isentropic table, m1 equal to 0.15 and gamma equal to 1.4. Then 4FL divided by D equal to 28.354 minus 1.069. Then then L equal to 308.85 meter. Then find out the pressure and the temperature at exits. P2 by P1 is equal to P2 by P star M2 divided by P1 by P star M1 is equal to 2.138 divided by 7.3193. Then find out the P2 by P1 equal to 100.773 kilopascal. Then find out the T2. T2 by T1 equal to T2 T1 star divided by T2 into T1 star. Then T2 equal to 297.59 Kelvin. Then find out the stagnation pressure loss. P02 equal to P02 divided by P02 star into P01 divided by P01 star into P01. Then P02 equal to 231.009 kilopascal. Then find out the P2 is equal to P2 divided by P star at M2. Then P1 by P star at M1 into P1 is equal to 2.629 divided by 4.3615 into 700. Then T2 equal to 1.161 divided by 1.185 into 333 is equal to 326.2557 Kelvin. Then C2 equal to 0.4415 divided by 0.272 into 0.25 root of 1.4 into 287 into 333. Therefore C2 equal to 148.432 meter per second. Therefore T divided by T star equal to 1.185. Next one, question number 3. Air is flowing in an insulated duct with a Mach number of M1 equal to 0.25 at a section downstream. In the entropy is greater by amount 0.124 unit as a result of friction. What is the Mach number of this section? The static property the inlet are 700 kilopascal and 16 degrees Celsius. Find velocity, temperature and the pressure at the exit. Find the properties of the critical section. So the given data is M1 equal to 0.25, S2 minus S1 equal to 0.124 kilojoule per kg Kelvin, P1 equal to 700 kilopascal, T1 equal to 60 plus 270. That is in terms of the Kelvin 333 Kelvin. We know that S2 minus S1 divided by R equal to minus ln of P01 divided by P02. Then S2 minus S1 divided by R is equal to ln of P01 divided by P02. Then ln of P01 divided by P02 equal to 0.124 divided by 0.287 is equal to 0.432. Then P01 divided by P0 equal to 1.54. From the isentropic table, M1 equal to 0.25 and gamma equal to 1.4. Therefore P01 divided by P0 equal to 1.54. Then T1 divided by T0 equal to 0.987. P1 divided by P01 equal to 0.957. Then T01 equal to 337.386. P01 equal to 731.452 kilopascal. From Fano table, gamma equal to 1.4. At gamma equal to 1.4, P01 divided by P02 is equal to 1.54. Then P01 divided by P0 star divided by P02 divided by P0 star equal to 1.54. Therefore P02 divided by P01 equal to 2.4065 divided by 1.54 4 to 1. Therefore, P02 divided by P02 equal to 1.5622. From the Pena table, divided by P0 star is equal to 1.5622. The corresponding Mach number M2 equal to 0.41. The velocity, pressure and temperature at the exit section are T star is equal to T0 divided by 1.185 is equal to 333 divided by 1.185. Therefore, T star equal to 281.01266 Kelvin. Therefore, then P divided by P star equal to 4.3615. Then finally, P star equal to 160.495 kilopascal. Then C star equal to root of gamma T is equal to 336.022 meter per second. The next topic, Rayleigh flow. Duct flow with the heat transfer and negligible friction. Flow in a constant area duct. Rayleigh flow, duct flow with the heat transfer and negligible friction. Flow in a constant area duct with the heat transfer and without friction is known as Rayleigh flow. Many compressible flow problems encountered in a practice involve chemical reactions such as combustion, nuclear reaction, evaporation and condensation, as well as heat gain or heat loss through the duct wall. Such problems are difficult to analyze. Essential feature of such complex flow can be captured by simple analysis method, where generation or absorption is modeled as heat transfer through the wall at the same rate. So this is the picture. It is a control volume. In certain engineering process, heat is added either by external sources across the system boundary, by heat exchanger, or internally by chemical reaction in a combustion chamber. Such processes are not truly adiabatic. They are called adiabatic process. Application. In the combustion chamber, inside turbojet engine usually have a constant area and the fuel mass addition is negligible. These properties make the Rayleigh flow model applicable for heat addition to the flow through the combustion, assuming the heat addition does not result in dissociation of the air-fuel mixture, producing a shock wave inside the combustion chamber of an engine due to thermal choking is very undesirable due to the decrease in a mass flow rate and thrust. Therefore, the Rayleigh flow model is critical for an initial design of the duct geometry and combustion temperature for an engine. The Rayleigh flow model is also extensively with the Fana flow model. These two models intersect at a point on the enthalpy, entropy and Mach number entropy diagram, which is meaningful for many applications. However, the entropy values for each model are not equal at sonic point state. The change in the entropy is 0 at m equal to 1 for each model, but the previous statement means the change in the entropy from the same arbitrary point to the sonic point is different for the Fana and Rayleigh flow model. Combustion process, regenerator, heat exchanger, intercooler. The following are the assumptions that are made for analyzing the such flow problem. One-dimensional steady flow. Flow takes place in constant area duct. The frictional effects are negligible compared to the heat transfer effect. The gas is perfect. Body forces are negligible. There is no external shock torque. There is no obstruction in the flow. There is no mass addition or rejection during the flow. The composition of the gas does not change appreciably during the flow. Rayleigh line occur. The frictionless flow of a perfect gas through a constant area duct in which heat transfer to or from the gas is dominant factor bringing about changes in the flow is referred to as Rayleigh flow or diabatic flow. In thermodynamic coordinate, the Rayleigh flow process can be described by the governing by a curve known as Rayleigh line and is defined as the locus of the quasi-static thermodynamic state point traced during flow. In the Rayleigh line satisfy the equation of state along with the symbol forms of continuity and momentum equation. Next one, governing equation. In order to formulate the equation for a rally line, let us consider steady flow of a perfect gas through a constant area of passage, in which transfer of heat with the surrounding is the major factor responsible for the changes in the fluid property. The simple form of the continuity equation for steady one-dimensional flow in a constant area duct is Ma equal to rho AC, then M by A equal to rho C, then G equal to Ma equal to rho C, where G equal to mass flow density, C equal to velocity absorption, rho equal to density of, then G equal to rho C. Then C equal to G by rho. Momentum equation is given by P plus rho C square equal to constant. Substitute C equal to G by rho, then P plus G square divided by rho square equal to C. Then P equal to G square B is equal to C. Specific volume B equal to 1 by rho. Equation 1 may be used for representing Rayleigh line on the Kensington diagram as illustrated in the figure shown in below. In general, most of the fluid in practical use have a Rayleigh curve of the general form shown in figure. So this is the Rayleigh line on Kensington diagram. The portion of the Rayleigh curve above the point of maximum entropy usually represents the subsonic flow, that is M less than 1, and the portion below the maximum entropy point represents supersonic flow, that is M is greater than 1. And entropy increases due to heat addition and entropy decreases due to heat rejection. Therefore, the Mach number is increased by heating and decreased by cooling at a subsonic speed. On the other hand, the Mach number is decreased by the heating and increased by cooling at supersonic speed. Therefore, like friction, heat addition also trend to make the Mach number in the duct approaches unity. Cooling causes Mach number to changes in the direction away from the unity. Rayleigh flow. Rayleigh flow refer to adiabatic flow through a constant area duct, where the effect of heat addition or rejection is considered. Compressibility effects often come into consideration, although the Rayleigh flow model certainly also apply to the incompressible flow. For this model, the duct area remained constant and no mass is added within the duct. Therefore, unlike fan of flow, the stagnation temperature is variable. The heat addition causes a decrease in stagnation pressure, which is known as the Rayleigh effect and is critical in the design of combustion system. Heat addition will cause both supersonic and subsonic Mach number to approach Mach 1, resulting in choked flow. Conversely, heat rejection decreases a subsonic Mach number and it increases a supersonic Mach number along that. It can be shown that for calorically perfect flow, the maximum entropy occurs at M equal to 1. A Rayleigh flow is named after John Strutt, third parent Rayleigh theory. So, a Rayleigh line is plotted on the dimensional sketches axis. The Rayleigh flow model begins with a different equation that releases the changes in Mach number with changes in stagnation temperature T0. The differential equation is shown below. This is the dm square divided by m square is equal to 1 plus gamma m square divided by 1 minus m square into 1 plus gamma minus 1 divided by 2 m square d T0 divided by T0. Solving the differential equation leads to relation shown below, where T0 star is the stagnation temperature at the throat location of the duct, which is required for thermally choking the flow. Therefore, T0 divided by T0 star is equal to 2 gamma plus 1 m square divided by 1 plus gamma m square whole square into 1 plus gamma minus 1 divided by m square. So, this is the next video. Thank you.